Hello everyone, welcome to my video. After relative velocity of rigid body, in this video, we will explore relative acceleration. When we were dealing with relative velocity, we have equations like VB equals to VA plus VB relative to A, where VB relative to A is always perpendicular to RB relative to A. From relative velocity, we can take further step to get relative acceleration by taking the derivative. If you have followed along in class and videos, you probably have noticed that all practice questions we did not ask us to solve any relative acceleration. This is because relative acceleration requires special attention, such as A and AB are not necessarily follow any pattern that is easy to determine their direction. For circular motions, one equation is not enough because it has both n and t direction to consider. Now, if you recall, relative velocity is easy to determine its direction as it's always perpendicular to the line connecting two points of interest. Unlike velocity, looking at the instant where AB is on the right, the acceleration of A and acceleration of B can be in any direction. However, because they are vectors, we can move them tail to tail based on the mathematical equation AB relative to A equals to AB minus AA. The vector here is exactly our A acceleration, AB slash A, B relative to A. So just like acceleration of A, there must be an n and t component of the acceleration B relative to A. We will do so by adding them here. You can see on the diagram on the right. Quick recap, acceleration B relative to A is given by AA and AB. At the same time, this acceleration B relative to A, it can be broke into A, B slash A, n component, and A, B slash A, t component. Okay, so this is demonstrated on the geometry on the right-hand side. I just made this geometry bigger so we can see it better. Based on the vector geometry, this equation can be written as AB equals to AA plus the n component of acceleration B relative to A and t component A, B slash A. If we just look at the term alone here, based on what we know about curvilinear motion, we can get the n component of the B relative to A acceleration is VB slash A square over R, or written as R omega format. And the t component of the acceleration B relative to A is R alpha BA. Here we can see the connection between the relative velocity V B slash A and the relative acceleration A B slash A. Then let's look at the vector format, using what we already know as well, but just applied to the relative acceleration format with the subscript B slash A, B relative to A. I reminded you about the vector direction before in lecture 22, so be careful to distinguish between the position vector B relative to A versus the RAB. The position vector needs to be pointing towards the point of interest. For example, our point of interest here is B, so it's pointing from A to B, so it's vector AB, or position vector B relative to A. If you forgot, please review lecture 22. Okay, I'm putting everything here together. On the left-hand side is what we have got from the demonstration on the previous slides, but they are B relative to A. That's what we did. So on the right-hand side, these equations are for A relative to B. Pretty much everything the same except A and B are reversed. Take a note here that alpha and omega is the same for either A relative to B or B relative to A because they are on the same object. We're just looking from the different angle here. For example, if this is A, this is B. When A looking at B rotating this way, this is clockwise, right? And then from B's perspective, if I'm looking at A, I'm still rotating, will be like that, still clockwise. So the clockwise or counterclockwise is the same for either A looking at B or B looking at A. Right? Try it yourself using a pen in your hand. As you can see, for relative acceleration problems, there are going to be a lot of variables and values. So here are some general tips. You will have to clearly identify knowns and unknowns, and you have 3 different methods that you can use: scalar, vector, or graphical. You need to choose a 1 or 2 convenient reference point, but you do not want to choose the instantaneous center of zero velocity because we need the acceleration in both n and t direction. If you choose that point, then you don't have the t direction acceleration. Okay, I'll do one example here. This is a sample problem 5/15 from your textbook. The textbook provided scalar and graphical solution, so please read them. Here I'm going to do this using vectors, so you can see how one problem can be solved in 3 ways. Then we look at link BO. Why BO though? Because point B is linked to A and the point B is linked to O, which we know about O already. And oftentimes you will see that it is a middle point we need to pay attention to. Plus we need the acceleration of B, as you can recall from the problem. AB can be written as ABN component plus the ABT component, where we know that the ABT component 0 because OB is rotating at a constant clockwise angular speed. For acceleration calculation, we will need the position vector. So let's get ROB. Using the geometry, ROB is 5/12 cos 60I plus 5/12 sine 60J. And since ABT component 0, we just need to solve for the n component, which equals to omega BO cross bracket omega BO cross ROB. We're just subbing everything here. And this is the final answer we got for acceleration of AB. We know about B now. Let's now use link AB back to find out A. Use the equations we derived for A/B n component equals to omega AB cross RBA, and subbing everything, including RBA, which can be found using the geometry of the triangle ABO. Note that the angle 18.02 was obtained from a previous question, so we'll just treat this as a known value here. Then we've got our acceleration of A relative to B, the n component, negative 1015.58 bracket negative cos 18.02I minus sine 18.02J. We'll solve the n part, and we'll need to get the t part. Use the equation we derived again. The A/B t component is alpha cross R. We do not know the alpha AB. That's fine. This is one of the unknown we need to solve. Just like AA, here we'll just set it as an unknown as alpha AB scalar K, assuming it's counterclockwise. Therefore, our relative acceleration A to B, the t component, is given by alpha ABK cross the RBA position vector. Subbing everything, we have one unknown here, the alpha AB in the equation. Remember, this is what we want. We are interested in the absolute acceleration of A. And this is the equation we need to use. AA equals to AB plus the n component of A/B and t component of A/B, the acceleration. Let's put everything together here to see if we got them all. At the beginning, we already set this up. We've got that. and we calculated the acceleration of b. We calculate the n component of a slash b, and we calculate the t component of a slash b. So it seems like we have everything with two unknowns, which is alpha AB and AA. We have two equations. We have four equations and two directions. So this is two unknowns with two equations, essentially. So this is entirely solvable. We'll sub in everything and get our final answer for the absolute acceleration of A and the angular acceleration of AB. Finally, you can see that we got a positive AA. That means our assumption is correct. It's the same direction as we assumed. But finally, we got a negative alpha AB. That means this is opposite to our assumption. I hope this video is clear and helpful for you to understand the relative acceleration. I created myself a cue card with all the equations on page 5 and just link each variable to the value given in each question. Please review the recommended readings as listed here. Thank you for watching. See you next time.